We're headed into our Beyond the Book chapter, which I'm going to call Chapter X, Solids of Revolution. We're going to be creating these solids that we create by revolving a certain function around an axis. So we're going to be creating these solids and calculating volume of these solids and also surface area. However, what we first need to look into is reviewing finding the area underneath the curve, because we're going to take this study, finding the area under a curve, and extending it to creating these solids of revolution. So the objectives that we're going to be doing today is just refreshing the link of integration with Riemann sums and finding the area under curves.
So this is an old test, and what we're going to be looking at and reviewing is how we once started out by approximating the area within a bounded region, so the area underneath the curve. So what was required was, first of all, knowing that we were approximating the upper sum of the area bounded by the x-axis. Keep in mind that the x-axis is the same thing as y equals 0. It's that horizontal line. So here that is, okay, the x-axis. So we also had this y equals 2x squared plus 1. You can see that is right here. I sketched that. It was a parabola because it was a quadratic, shifted up 1, and then instead of going over 1 up 1, because of this scale factor of 2, we went over 1 up 2. So that's this point right here. So I should be 1, 2, 3. Alright, the other thing is we needed to bound this area over a certain interval. So we only wanted to look at the area between x equals 0 and x equals 1. So I went ahead and drew those vertical lines in as well. So what you're seeing here is we're trying to find the area, and you can see this kind of goofy looking shape. It's a four-sided figure with a curved side, and we don't have any formula like we do a rectangle or a triangle to figure out, oh, what is the area of this goofy shape. So that's where we're left to use the Riemann sum to approximate it. And eventually we turn this into integration, but we're reviewing the use of the Riemann sum. What I am going to do is we're going to let this n equal 2. We're going to break this up into rectangles because we have an area, or area formula for rectangles. So we can calculate the area of rectangles, and we're going to make 2 of them. That's where this n equals 2. So what that tells us to do is we're separating this interval from 0 to 1 into 2 equal pieces. So there we have it. I've split it there. Let's review this Riemann sum. What this means, the sigma sign means sum. Okay, and then here's our index number. What I basically stands for is the rectangle number that you want to look at. So we would be adding up rectangle 1. What is the area of rectangle 1? What is the area of rectangle 2 if I equal 2? If I equal 3, we would be looking at rectangle 3. What's the area of rectangle 3? All the way up until the nth rectangle. In this case, we're only looking at 2 rectangles, so we would be going from I equals 1 to 2, finding the area of the first and the second rectangle that we create. The other thing is we're going to be looking at, obviously, then the height. This is the height, f of c sub I, so of our first rectangle and our second rectangle. So the height of the rectangles, and these are the widths. This is delta x, it's the change in x or the width of these rectangles. So what we can see here is, I just want to review, this right here is delta x, it's going to be a width of a rectangle. So here I'm going to review that delta x is actually equal to b minus a over n. So it's the interval that you're looking at divided by how many pieces you're dividing that into. So in this situation, we're going to be looking at delta x is 1 minus 0 over 2, which is just 1/2. Okay, and you can see that clearly here, that the widths of our rectangles are going to be 1/2. The other thing that we want to look at is that c sub I that you see here. This takes some studying. C sub I, there is no kind of clean formula that I can give you for that. However, one thing that is often used is A, it's wherever you're starting, plus, and then delta x times I. So in this case, what we are going to be using, C sub I is the study of the x values that you're going to try to find the heights with. You need to be able to try to calculate where these y or these heights are by use of these certain increments. And what you'll see is C sub I is directly related to delta x. This is kind of a general formula that you can use. So in this particular instance, c sub I is equal to 0 plus and then 1/2. So in other words, it's just going to happen every 1/2 of the way is where we're going to be calculating the heights. Alright, so now to go over these rectangles. I could use the left-hand sides of these tick marks that I've created along this curve. However, I'm not going to want to be making rectangles like this. Okay, and the reason why that would be using the left-hand sides that I've created of these intervals, it's because we want the upper sum. And what the upper sum is actually, it's an over approximation. And what you can see here is we have this empty space. This would be an under approximation. This would be the lower sum. So what I am going to do is I am going to use the right-handed sides of these increments or of these intervals that we've created. So I'm going to go all the way up from the c sub I location to the height of my curve, and I'm going to form my rectangle that way. And once again, we're going to get an over approximation, but that's why this is an approximation. Here is c sub 2. It's going to be our second rectangle's height. We're going to go all the way up to that curve and then draw our rectangle over. So there we have it. So now what I want to do is just add up what is the sums of these rectangles areas. So to do that, I'm going to use this completely. So I'm going to fill in everything that I know here. I'm always going to start at I equals 1, and then I'm going to go up to 2 because that's what my n is. I will need f of, and then here I'm just going to plug in my c sub I, which is going to be that 0. Oh, I'm sorry. I forgot to multiply this by I. So this is going to be times I. Sorry. So here I'm going to have 1/2 I. And then times our delta x, which we calculated over here, is just 1/2. And you can see that this is going to work out for each one of my rectangles. Because now if I plugged in my first index, I'm going to start with 1. So in other words, I'm going to find the area of rectangle 1. Area of rec 1. Okay, so if I plug that in to my formula, this is just going to be f of 1/2 times 1 times 1/2. And then this is going to be going into my formula. So you need to actually find out what is my height of this rectangle, which you could find by plugging in this interval or this c sub 1. So that is just going to be 1/2. So we get f of 1/2, which you're going to have to plug in here. We have 2 times 1/2 and then times 1, but we can just say that it's 1/2 now. 2 times 1/2 squared plus 1. That was me plugging in this 1/2 into my function. And then times the width, there's the width of the rectangle. Okay, so when you do that calculation, you are going to get 3/4. Okay, I'm also going to do rectangle 2 now because I'm going to have to also sum up the area of rectangle 2. So this is going to be f of 1/2 times 2, so 1/2 times 2 times 1/2. So now it's going to look something like this. The height, when I plug this in, this is 1/2 times 2, which is just 1. So we're going to plug in 2 times 1 squared plus 1 into my function here, which would have been the height at that one location, or at 2 delta x's over, okay, times 1/2. So when you do all of that, this is going to just be 1.5, sorry, 1.5. Okay, and then don't forget this means sum or sigma, so I'm going to add those together. What we're going to get is 2 and 1/4 units squared, or squared units. There's our answer. So what I would like to show you is what we just did is this first image right here. We let n equal 2, so in other words we use 2 rectangles to approximate the area within this bounded region. In that case our intervals were 1/2, and what we would have to use is these sub-interval or particular x values that were along those increments to plug into our formula to find also the heights. So we were not only using the delta x's, but we were using these c sub I values to plug into the function to get the heights. Over here what you're going to see is n equals 3, so in other words this is going to be 1/3, this is 2/3 because it would be 1/3 times 1. This would be 1/3 times 2, 1/3 times 3, so those would be all our c sub i's. This one, n equals 4. And this one, we're going to just let n equal n. We're going to actually eventually let n equal infinity by use of a limit process. But what you can kind of see here is if we let n equal infinity, these widths are going to be infinitely small because I have 1 minus 0, just like I calculated for something like this, 1 minus 0 divided by n, which is 4. If you had 1 minus 0 divided by n, which is infinity, well then it's essentially 0. But we can't really have a rectangle with the width 0, so we use this calculus or this limit approach that you're going to see me do here in a second to get the exact approximation underneath this area. And that is one of the great things about calculus, allowing us to find these areas of these funny or goofy shaped figures. This was the second problem to the test, and it said find the area of the bounded region using the limit definition of area. So we use the Riemann sum, but in this case we let n equal n, and then what we do in the end is calculate the limit, because of course we can't just necessarily sub in infinity for n, because infinity is something that's kind of ungraspable, except for if we have a limit, because then we can say, alright, if n were equal to 0, this whole thing is going to equal what? So we're going to set up the same thing, except for my delta x this time has changed because we're not letting n equal 2. We're going to do b minus a. Here is the same interval, and we're going to divide it by n this time. We're just going to let n equal n. So delta x is just going to be 1 over n. C sub I in this case, those x values that are going to help us find the heights of these rectangles, it's going to be our a plus and then delta x times I. So I'll do that right this time. It's going to be 0 plus 1 over n times I. So it's going to be I over n. So I'm going to plug this into this limit formula. We're going to have the limit as n approaches infinity. Alright, so I plugged that in completely, and what I would have you notice is I haven't really used this yet, so I'm going to actually plug that into my function here. And here's where I'm going to have 2 times, and then I over n squared plus 1. So I plugged in this just like I did in that previous example, but this time we do have an n in it, which is okay. That's what we're wanting. And then 1 over n is the widths of these rectangles. So here is what I'm going to have to simplify and solve using some properties that we have in our textbook. One of the page numbers is page 220. They're just properties of limits. And you can always look back in my videos at section 3.3. That also has these properties in it. So 3.3 is what section or chapter that I was looking at for those. Another one of the properties that we'll be using is found on page 399. This is section 6.2, so you can also look back to when we use that in section 6.2 of these videos. But they're going to be the summation formulas. And the one in particular that I'm going to use with this one, I'm just going to write it here off to the side. If we ever have the sum as I equals 1 to n of I squared, what that actually amounts to being is 2n cubed plus 3n squared plus n all over 6. So we're going to use that when we get to it. Eventually we're going to take out all of these sigma signs and replace them with these formulas. So I'm going to work this using the properties that you'll find on those 2 pages or in those sections of the videos. And so what I am first going to do is simplify this expression and distribute this 1 over n to everything. So alright, so now that I have this all simplified, what I am also going to do is I'm going to use one of the properties that says that if I were just to focus on this, that I can take that sigma sign and use it just like the sum and difference rule. I can just take it and go term by term. So I'm going to change colors for this part. This is where I'm actually using some of those properties that I listed off to the side. So that's this thing right here that I just went ahead and basically distributed that sigma sign if you could distribute it. But really it's just using the property that you can go term by term as long as you were adding. Okay, so now what I'm going to do, I'm going to move this over because I'm probably going to run out of room here. So the other thing is
what you're going to notice is my index number, the thing that's constantly changing is the I. So you're going to be plugging in, for example, the first thing would start with index 1. You would plug in 1 for the I. It would be 2 times 1 squared all over n cubed. You plug in I equals 2 the next time, so 2 squared over n cubed. This n is never changing, it's this I that's changing. So everything else is staying the same. I'm going to pull all of those constants out because the index is what I want to isolate. Because you're going to see here I'm aiming for this. So I'm going to change colors again to indicate that this is kind of a new idea. We are going to be using the property to pull out any constants. So here I'm going to pull out 2n cubed, and then just look at this as the sigma, or the sum, of I squared. Same thing here, 1 over n. There's nothing that's changing about that, so I'm just going to pull out that 1n. What's left is just a constant of 1. Okay, so now I am able to plug in these formulas. And let's see here, I'm going to have to move down. So I'm going to plug in this formula right here. What I have is an I squared. I also had a constant I never told you, but what that is just going to be is 1 times and then n. So however many times that you're, let me write that. The other one that I did not include here is if you ever have a constant, so some sort of constant, and you're going from I to 1 to n, what that just equals is whatever that constant is times n. So I'm going to also use that here. I'm going to use this formula and this formula in this next step here. So the limit as n approaches infinity of, and then here, out with this, in with this. So 2 over n cubed. And then, alright, so we're going to do the limit as n approaches infinity now, and I'm going to distribute this all through. 2n cubed plus 3, oh darn it, it's going to be 4n cubed plus 6n squared plus, and then distributing that 2 all the way across, 2n all over 6n cubed plus this one is just going to basically cancel each other out here. We're going to get just 1. Alright, so here now is another property that I did not talk about that you're going to have to refer back to, but it is chapter 5.5. So here off to the side I have a list of all the things that you're going to have to refer back to. And 5.5 is where you can look back for the video, but in order to calculate the limit as n approaches infinity, what you can do is something where you look at the degree on the bottom, it's an n cubed, and you're going to divide that highest degree by everything that you have here. So when you rewrite this, what you're going to be looking at is the limit as n approaches infinity of, these cancel each other out, so we just get 4, plus these are going to get 6 over, and then this simplifies to be just over n, plus, and then these will cancel each other out, we get 2 over n squared all over 6 plus 1. And now is that moment where if you were able to plug in infinity for all these n's, what you're going to have is this one rule that says if you have a limit as n goes towards infinity of any kind of constant over and then n to some sort of power, we'll say to the r, what's going to happen is this thing is essentially 0. It is equal to 0 because, think about it, 1 over or some sort of number over this ever increasing number, it's going to get smaller and smaller and smaller, so therefore when you could reach infinity it would be 0. So here what we're going to get is when I simplify this piece right here, all of this, and you can go limit this thing, you can distribute that limit as well, so the limit as n approaches infinity of, I'm sorry, I'm just going to write it right here, limit as n approaches infinity, because that's just going to stay the same. As n is increasing, 1 is just going to be 1. So this is going to become 0, this is 0, we get 4/6 plus 1, that's all going to just equal 1 and 2/3. You can see here in our original problem, we way overestimated it. but that's okay. It was a upper sum, so it was an upper approximation. Right here, what we just found is the actual area underneath that curve. So 1 2/3 is what we were looking for.